August 29, 1907, Quebec City. The engineering reports from Theodore Cooper's office would never fully capture what happened 1,250 feet above the St. Lawrence River that morning. Mohawk ironworkers, walking steel beams with methods that defied everything European engineering schools said was necessary for high-altitude construction safety. Through the hiss of pneumatic hammers and the screech of lifting cables, skilled riveting gangs moved across narrow steel spans with coordination that seemed impossible to university-trained observers. No safety harnesses, no elaborate scaffolding systems, no months-long apprenticeship programs, European methods required. Yet they drove red-hot rivets at 15,730 pounds per square inch, with precision European-trained crews could not match. In European construction, master ironworkers required years of formal education to work above 200 feet. Each project demanded extensive safety equipment, detailed engineering supervision, and acceptance rates below industry standards. Most carried budgets only wealthy developers could afford. The Mohawks were operating with training philosophy the Europeans had never imagined possible: systematic knowledge transfer, hands-on mentorship, cultural accountability that connected every apprentice to generations of experience. 800 miles from European engineering schools, the most decisive construction innovation in American history was revealing itself, not in superior equipment, not in advanced safety technology, but in the methodical training system that prepared every Mohawk ironworker for heights European methods never imagined conquerable. The St. Lawrence River cut through eastern Canada like a frozen blade in January 1886, its surface locked under 3 feet of ice that would crush conventional pier construction for the next 5 months. 58 feet down, the river bottom held the twisted remains of 2 previous attempts to span this 1,800-foot gap, the critical link that would complete the Canadian Pacific Railroad's transcontinental route. Without this bridge, freight trains carrying prairie wheat to Atlantic ports would remain trapped on the western shore, unable to reach the markets that could transform Canada's economy. Theodore Cooper stood in the offices of Dominion Bridge Company in Montreal, studying engineering drawings that represented the most ambitious cantilever span ever attempted in North America. At 52, Cooper commanded respect as America's most prestigious structural engineer, a man whose theoretical calculations had solved bridge problems from the Mississippi to the Hudson. His wire-rimmed spectacles reflected the lamplight as he traced stress diagrams with his finger, calculating load distributions that would allow steel beams to carry their own weight across impossible distances. The mathematics were elegant, the engineering sound, but one problem remained unsolved: finding enough skilled ironworkers willing to drive red-hot rivets 300 feet above the ice. "Men who want to rivet are rare," declared James Stewart, Dominion Bridge's site supervisor, his breath visible in the unheated office. And men who can do it at these heights are even rarer. The work demanded 4-man gangs capable of handling rivets heated to 2,000 degrees Fahrenheit, caught in metal buckets, and driven through steel beams 42 feet long at pressures exceeding 15,000 pounds per square inch. Each connection required split-second coordination between the heater firing his portable coal forge, the sticker in catching molten metal in flight, the bucker-up bracing the rivet head with his dolly bar, and the riveter wielding the pneumatic hammer that would forge the permanent connection. A single mistake meant death, either from falling or from superheated steel. Cooper adjusted his spectacles and pointed to the labor budget. European-trained ironworkers commanded premium wages, often $3 per day compared to the $1.50 that general construction workers earned. With the railroad company demanding cost controls and the brutal Canadian winter limiting the construction season to 7 months, Dominion Bridge faced an impossible equation: hire enough skilled workers to complete the project or abandon the most important transportation link in Canadian history. Stewart shifted uncomfortably in his chair. "We've been thinking about using some of the local Indians just for hauling materials, you understand. There's a reserve called Kanawake about 10 miles downriver. They're looking for work, and they'd come cheap." Cooper nodded absently, his attention focused on the stress calculations that would determine whether 30-ton steel sections could cantilever safely across the river. The idea of using local Mohawks as day laborers made financial sense. They could unload supply barges and carry tools, while the real ironworkers handled the skilled connections. It was a pragmatic solution to a budget problem, nothing more. Work began in March 1886, as soon as the ice cleared enough for supply barges to navigate upstream from Montreal. The first gang of Mohawk laborers arrived from Kanawake Reserve on a Tuesday morning, 12 men ranging in age from 19 to 45, dressed in canvas work pants and heavy wool shirts. They had been hired to unload structural steel from the barges and carry it to the base of the construction towers, simple manual labor that required no training and minimal risk. By the end of the first week, something unexpected was happening. Instead of remaining at ground level with the supply operation, several of the Mohawks had begun climbing the partially completed structure, walking out onto the steel beams that projected over the river like enormous diving boards. John Diabo, 27 years old with calloused hands, that showed years of physical work, balanced easily on an 8-inch wide beam while studying the riveting process taking place 50 feet away. His focus was intense, methodical, as he watched the 4-man European crew heat, catch, position, and drive each rivet. "Get down from there!" shouted a site foreman. "You're not supposed to be on the steelwork." Diabo ignored the order, instead moving closer to observe the pneumatic hammer operation. He seemed particularly interested in how the riveter judged the proper pressure and duration for each connection, watching the man's grip on the hammer and the angle of approach that ensured the rivet head formed correctly. When the gang moved to the next connection point, Diabo followed, maintaining his position on the narrow beam with an ease that made the watching foreman nervous. Similar scenes played out across the construction site, as more Mohawks abandoned their assigned material handling duties to study the ironwork. They asked technical questions about stress loads, thermal expansion, and connection methods, questions that surprised the European-trained foremen with their sophistication. Louis Deere, a stocky man in his 30s, wanted to know why certain beam connections used 6 rivets while others used 8. Joe Jacobs, barely 21, asked about the relationship between rivet temperature and the final strength of the joint. The European iron workers found the attention unsettling. These were trade secrets learned through years of apprenticeship, not casual information to be shared with untrained laborers. But the Mohawks persisted, observing every aspect of the operation with systematic attention that went far beyond mere curiosity. Stewart watched this development with growing concern. His construction schedule depended on maintaining clear distinctions between skilled and unskilled labor. If the Mohawks continued interfering with the riveting operations, productivity would suffer. But when he complained to Cooper during their weekly progress meeting, the chief engineer dismissed the problem with a wave of his hand. "Let them watch if they want," Cooper said, not looking up from his calculations. "As long as they're not interfering with the real work, I don't see the harm." What Cooper failed to recognize, what his engineering education had never prepared him to understand, was that systematic observation was itself a form of training. The Mohawks weren't simply watching. They were learning, analyzing, and beginning to develop their own understanding of high steel construction that would soon challenge everything European methods had established as fundamental truth about ironwork at impossible heights. By October 1886, the St. Lawrence Bridge project had produced an unexpected outcome that Theodore Cooper's engineering calculations had never predicted. 12 Mohawks from Kanawake Reserve had been trained as skilled ironworkers, their systematic observation transformed into hands-on expertise that rivaled crews with years of European apprenticeship. What had begun as a cost-cutting measure, hiring local labor for material handling, had evolved into something that challenged fundamental assumptions about how high steel skills were acquired and transmitted. The transformation hadn't happened by accident. John Diabo, who had first climbed the steel beams to observe the riveting process, had been quietly recruited by site foreman James Mackenzie after demonstrating an intuitive understanding of load distribution that impressed even the skeptical Europeans. Within 6 weeks, Diabo could catch red-hot rivets thrown across 30-foot gaps with the precision of men who had trained for years in Glasgow shipyards. But more significantly, he had begun teaching other Mohawks the systematic approach he had developed through his methodical observations. Louis Deere became Diabo's first apprentice. learning not just the physical mechanics of riveting, but the subtle indicators that separated competent work from dangerous failure. Deere discovered that properly heated rivets produced a specific sound when struck, a clear, ringing tone that indicated the metal had reached the correct temperature and malleability. Incorrectly heated rivets produced a duller sound and often failed under stress, creating weak points that could cascade into structural failure. This auditory quality control, never mentioned in engineering textbooks, became part of the knowledge base that Mohawk systematically transferred from experienced workers to apprentices. The process extended beyond individual skill acquisition. When the Sioux Bridge project began in 1887, spanning the St. Mary's River between Michigan and Ontario, the Dominion Bridge Company specifically requested Mohawk ironworkers for the high-altitude connections. But the Mohawks didn't arrive as individuals seeking employment. They came as organized crews that included experienced riveters and deliberate apprentices. Each four-man gang brought one trainee from Kanawake Reserve, creating a systematic pipeline that ensured knowledge transfer continued across multiple construction sites. Joe Jacobs, the young man who had asked technical questions about rivet counts and connection strength, emerged as a particularly skilled heater, capable of maintaining forge temperatures within the narrow range required for optimal rivet malleability. Working with portable coal forges that had to be constantly fed and adjusted, Jacobs developed techniques for reading flame color and adjusting airflow that produced consistently superior results. His method involved monitoring not just the visual appearance of the heated metal, but the subtle changes in sound as the rivet reached proper temperature, innovations that European-trained heaters had never systematically developed. The communication patterns that emerged on Mohawk crews puzzled and sometimes frustrated European foremen. The men spoke to each other in their native language while working, using precise terminology that had no English equivalents for describing steel stress patterns and connection quality. When a bucker-up needed to signal that a rivet was properly positioned, he used a specific Mohawk phrase that conveyed not just readiness, but the exact angle and pressure required. These weren't casual work conversations, but technical communications developed specifically for high steel coordination. Thomas Deere, Louis's younger brother, joined the crew working on the Sioux Bridge in 1888 as an apprentice sticker-in, the crew member responsible for catching red-hot rivets thrown from the forge. The position demanded exceptional hand-eye coordination combined with precise timing. A rivet that cooled too much before placement would create a weak connection, while one caught improperly could cause severe burns. Thomas learned by practicing with cold rivets first, developing the reflexes and positioning that would keep him alive when working with molten metal 300 feet above the river. What European observers failed to recognize was that this apprentice system operated according to cultural accountability structures that extended far beyond individual job performance. Each Mohawk worker represented not just his own reputation, but the standing of Kanawake Reserve in the broader construction industry. Failure or carelessness by one crew member reflected on the entire community's reliability, creating social pressure for excellence that no European employment contract could match. By 1890, more than 30 skilled Mohawk ironworkers operated across construction sites from the Great Lakes to the Atlantic provinces. Each crew maintained its apprentice system, ensuring that knowledge accumulated rather than remaining static. When experienced riveter Peter Angus developed a technique for detecting stress fractures in steel beams by running his hand along the surface, feeling for microscopic irregularities that indicated potential failure points, the tactile knowledge was systematically taught to younger workers who would carry it to new construction sites. The economic implications were becoming impossible to ignore. Mohawk crews consistently outperformed European-trained gangs in both productivity and quality metrics. Where traditional crews struggled to place 200 rivets per day while maintaining acceptable standards, Mohawk teams routinely completed 300 to 400 connections with rejection rates below 2%. Their efficiency stemmed not from reckless speed, but from systematic preparation and coordination that eliminated the delays and corrections that plagued less organized crews. European engineering supervisors began requesting Mohawk workers specifically for challenging high-altitude projects, but they continued to frame this preference in terms of natural ability rather than acquired skill. The GOAT theory, persisted because it was psychologically easier than acknowledging that systematic training methods developed outside formal engineering education might be superior to European apprenticeship traditions. Admitting that Mohawks had developed innovative approaches to high steel work would have required questioning assumptions about technical expertise that formed the foundation of European engineering authority. As construction projects grew more ambitious and heights more extreme, the demand for workers willing and able to perform precision ironwork at dangerous elevations continued to exceed supply. Theodore Cooper, now planning his masterpiece Quebec Bridge, with a main span of 1,801 feet, faced the reality that his project would require more than 70 skilled ironworkers capable of driving rivets at heights that few European-trained men would attempt. The systematic training methods developed by Mohawk crews represented the only reliable source of workers with the specific skills his unprecedented engineering challenge would demand. Theodore Cooper's Quebec Bridge represented the pinnacle of early 20th century engineering ambition, a cantilever span stretching 1,801 feet across the St. Lawrence River, longer than any bridge previously constructed. From his office in New York City, Cooper had refined his calculations to achieve this record-breaking distance while using 40% less steel than conventional engineering standards recommended. The mathematical elegance satisfied his theoretical requirements, but the actual construction demanded precision ironwork at heights and stresses that pushed both materials and workers beyond previously tested limits. By August 1907, the bridge's southern cantilever arm extended 548.6 meters from its support tower, carrying 86 workers across steel beams that vibrated with each gust of wind off the river. The structure had reached the critical phase where its own weight began creating stresses that Cooper's reduced steel design was barely adequate to handle. Compression cords 24 inches wide bore loads approaching their theoretical maximums, while the connections between these massive beams depended entirely on the precision of rivets driven by crews working hundreds of feet above the water. Jean-Baptiste Beauvais, a skilled Mohawk riveter in his third year on the Quebec Bridge project, began his shift on the morning of August 29th by inspecting the connections his crew had completed the previous day. This systematic quality check had become standard practice among Mohawk workers, a methodical verification that went beyond the cursory inspections European-trained crews typically performed. Beauvais ran his hands along rivet heads, feeling for the subtle irregularities that indicated incomplete connections or stress concentrations that could propagate into larger failures. At approximately 10:30 that morning, Beauvais discovered something that stopped him cold. A rivet he had personally driven 18 hours earlier, a connection he had tested and approved using the auditory and tactile methods perfected through years of systematic training, had snapped cleanly in two. The failure wasn't from improper installation or inadequate heating. The rivet had been driven correctly but had fractured under stresses that exceeded the design specifications Cooper's calculations had established as safe. Beauvais immediately called to the nearest foreman, pointing to the failed connection while other crew members gathered around the evidence. The broken rivet represented more than a single faulty component. It indicated that the entire structure was experiencing loads beyond its engineered capacity. But before the implications could be fully assessed, before emergency procedures could be implemented, the screaming of twisted steel began echoing across the construction site as 24-inch compression cords buckled under stresses they were never designed to handle. The collapse occurred with terrifying efficiency. The southern cantilever arm, carrying its full complement of workers and equipment, began falling toward the St. Lawrence River as steel connections failed in rapid succession. Beauvais, standing near the center of the span when the failure began, had perhaps 3 seconds to react before the entire section plunged toward the water. His systematic training included crisis response protocols that European-educated workers had never developed, methods for surviving structural failures that Mohawk crews had refined through generations of dangerous high-steel work. As the bridge section twisted during its 15-second fall, Beauvais managed to position himself near a section of decking that would provide some protection when the wreckage hit the river. His understanding of how steel structures behaved under extreme stress, knowledge acquired through hands-on experience rather than theoretical study, enabled him to make split-second decisions that saved his life while dozens of other workers were crushed by falling beams or trapped beneath twisted metal when the debris reached the river bottom. Of the 86 workers on the span when the collapse began, 75 died instantly or drowned in the aftermath. The casualties included 33 Mohawks from Kanawaki Reserve, skilled ironworkers whose systematic training methods had made them the most reliable high-steel crews in North America. These weren't inexperienced laborers who had made fatal mistakes. They were the most competent structural workers available, killed by engineering failures that no amount of practical skill could have prevented. Beauvais survived with a broken leg and severe bruising, pulled from the wreckage by rescue crews who found him floating near an overturned section of bridge decking. During his recovery, he provided detailed testimony about the structural warning signs that had become apparent in the hours before the collapse. His account documented the systematic quality control procedures that Mohawk crews used to detect potential failures, procedures that had identified the snapped rivet but hadn't been implemented early enough to prevent the catastrophic outcome. The subsequent engineering investigation revealed that Cooper's design had pushed the structural limits beyond safe margins in pursuit of record-breaking span length and cost reduction. The bridge had failed not because of worker error or inadequate construction techniques, but because the theoretical calculations had underestimated the dynamic stresses created by wind loads and thermal expansion acting on such a massive cantilever structure. The Mohawk workers had performed their jobs with characteristic precision. The engineering specifications they were required to follow had been fundamentally inadequate. The disaster's aftermath provided unexpected validation of Mohawk training methods. Surviving foremen reported that during the collapse and rescue operations, Mohawk crews had maintained discipline and coordination while European-trained workers abandoned safety protocols in panic. The systematic crisis response training that was part of traditional Mohawk ironwork education had prepared workers to function effectively even during catastrophic structural failures, skills that no engineering school curriculum had ever addressed. The Quebec Bridge collapse killed more skilled Mohawk ironworkers in a single day than had died in the previous 20 years of high-steel construction. The loss represented not just individual tragedies, but a devastating blow to the systematic knowledge transfer process that had made Mohawk crews the most reliable source of precision ironwork in North America. Kanawaki Reserve had lost an entire generation of experienced workers whose expertise in high-altitude construction had taken decades to develop and could not be quickly replaced. The engineering establishment's response focused on revised calculations and improved design standards, but it largely ignored the human factors that had contributed to both the disaster and the survival of workers like Beauvais. The systematic training methods that had enabled Mohawk crews to outperform European-educated workers remained dismissed as natural ability rather than acquired expertise, even as evidence mounted that their crisis response protocols and quality control procedures were superior to conventional construction practices. As news of the Quebec Bridge disaster spread throughout the construction industry, the fundamental question remained unresolved: whether the tragedy had discredited Mohawk ironwork methods or had instead demonstrated that systematic practical training was essential for construction projects that pushed engineering limits beyond the safety margins that theoretical calculations could guarantee. The clan mothers of Kanawaki Reserve convened an emergency session 3 days after the Quebec Bridge disaster, their deliberations carrying implications that would reshape American construction for the next century. These women, led by Sarah Diabo, whose son John had been among the first Mohawks trained as an ironworker, and Mary Jacobs, whose family had lost 2 skilled riveters in the collapse, possessed authority within Mohawk governance that European observers consistently underestimated. Their decisions regarding community welfare and economic strategy carried the force of law within the reserve, and their analysis of the Quebec disaster focused on systematic risk management rather than emotional reaction. The mathematics were stark and undeniable. 33 skilled Mohawk ironworkers had died in a single afternoon, representing nearly half of Kanawaki's most experienced high-steel crews. These weren't easily replaceable workers, but men whose expertise had been developed through systematic training that required years to complete. The knowledge they carried, methods for detecting steel stress patterns, techniques for maintaining quality control at dangerous heights, crisis response protocols that had kept Mohawk crews safer than their European counterparts had been partially lost with their deaths. Sarah Diabo articulated the strategic problem with characteristic directness during the clan mother's second day of meetings. "We cannot allow so many skilled men to work on one project again," she declared, her words carrying the authority of someone whose family had been building bridges since the first St. Lawrence River project in 1886. "When they all work together, they all die together." The observation wasn't driven by grief, but by cold analysis of how concentrated risk exposure threatened the survival of systematic knowledge that had taken 2 decades to develop. The clan mother's solution emerged from their understanding of both engineering principles and economic necessity. They instituted what would become known as the booming out rule, a deliberate dispersal strategy that would prevent large concentrations of Mohawk ironworkers on any single construction project. Instead of allowing crews to work together on prestigious assignments like the Quebec Bridge, skilled workers would be scattered across multiple sites throughout North America, reducing catastrophic risk while simultaneously spreading their training methods across a broader geographic area. This decision represented sophisticated systems thinking that European engineering education had never addressed. The clan mothers recognized that Mohawk ironwork expertise had become essential to American construction capability, but they also understood that this expertise was vulnerable to single-point failures like the Quebec disaster. By dispersing skilled workers across numerous projects, they could ensure both community survival and continued knowledge transfer while maintaining the systematic training methods that had made Mohawk crews superior to European-educated competitors. The implementation of the booming out strategy began immediately as surviving ironworkers completed their recovery from the Quebec disaster. Joseph Deere, whose brother Louis had died in the collapse, accepted a position with the American Bridge Company working on railroad spans in Pennsylvania. Peter Angus, the experienced riveter who had developed techniques for detecting steel stress fractures through tactile inspection, joined a crew building industrial structures in Chicago. Each man carried with him the systematic training methods that had been refined through 20 years of high steel construction, along with new crisis response protocols developed from analysis of the Quebec Bridge failure. By 1910, Mohawk ironworkers had established presence in construction markets from San Francisco to Boston, their systematic training methods adapting to regional differences in materials and techniques while maintaining the core principles of hands-on knowledge transfer. Each 4-man crew continued to include one apprentice from Kanawake Reserve, ensuring that skills development remained connected to the cultural accountability structures that had produced consistently superior results. The geographic dispersal strategy had transformed a community-based training program into a continent-spanning network of expertise. The timing of this dispersal coincided with the beginning of America's most ambitious construction era. By 1920, New York City had entered what newspapers termed the race to the sky, with multiple developers competing to build the world's tallest structures. The Woolworth Building's 792 feet had established the benchmark that ambitious architects were determined to surpass, but achieving greater heights required precision ironwork at scales and elevations that pushed existing construction capabilities beyond proven limits. 3 projects emerged as the primary competitors in this vertical race. 40 Wall Street, designed to reach 840 feet, represented traditional approaches to skyscraper construction using proven engineering methods and conventional labor practices. The Chrysler Building, originally planned for 808 feet, but later expanded to 1,046 feet with its distinctive metallic spire, demanded innovative approaches to both structural design and high-altitude assembly. Most audacious of all, the Empire State Building project announced plans for a structure reaching 1,250 feet, including its mooring mast, a height that would require construction techniques that had never been tested under real-world conditions. These unprecedented heights created demand for ironworkers capable of maintaining precision and safety standards, while working under conditions that exceeded anything in previous construction experience. Wind loads at 800 feet created stresses and vibrations that could fatigue both materials and workers. Thermal expansion at such heights required connection techniques that could accommodate movement while maintaining structural integrity. The logistical challenges of lifting 30-ton steel beams to these elevations demanded coordination between riveting crews and crane operators that left no margin for error. European engineering firms submitted bids for these projects, but experienced construction supervisors understood that success would depend on securing skilled ironworkers willing and able to perform precision work at impossible heights. The systematic training methods that Mohawk crews had developed, techniques for reading steel stress patterns, protocols for maintaining quality control under extreme conditions, crisis response procedures refined through decades of dangerous work, represented the only proven source of expertise capable of meeting the technical demands these projects would require. Paul Starrett, whose construction company had secured the contract for the Empire State Building, recognized that completing 1,250 feet of structural steel in 410 days would require the most skilled ironworkers available in North America. His project specifications called for 38 riveting gangs working simultaneously across multiple floors, coordinating with 9 derricks, lifting massive steel sections while maintaining the precision standards that would ensure structural integrity. The Clan Mother's dispersal strategy had positioned experienced Mohawk crews throughout American construction markets at precisely the moment when their systematic expertise would be tested by the most demanding project in the history of high steel construction. Empire State Inc. announced specifications in January 1930 that would test every assumption about high steel construction capabilities in North America. The building would rise 1,250 feet above Fifth Avenue, requiring 57,000 tons of structural steel assembled by 38 riveting gangs working simultaneously across multiple floors. The construction schedule allowed 410 days from excavation to completion, demanding coordination between workers, materials, and equipment at scales that had never been attempted in the history of urban construction. Paul Starrett understood that conventional European-trained crews could not deliver the precision and speed his timeline demanded. The project required ironworkers capable of maintaining quality standards while placing rivets at rates that traditional apprenticeship methods had never achieved. His labor recruitment strategy focused specifically on securing Mohawk crews whose systematic training had produced the most reliable high steel workers available, despite their geographic dispersal following the Quebec Bridge disaster 23 years earlier. The first structural steel reached the construction site on March 7, 1930, delivered by trucks that navigated through Manhattan traffic to deposit 30-ton beams at the base of 9 derricks positioned around the building's perimeter. These derricks, each capable of lifting loads to heights exceeding 1,000 feet, represented the mechanical advantage that would enable rapid vertical assembly, but their effectiveness depended entirely on the coordination skills of riveting crews working at the upper reaches of their lifting capacity. Joseph Diabo arrived from Detroit on March 15th with a 4-man crew that included his nephew Louis, a 24-year-old apprentice whose training had begun 6 years earlier on bridge projects spanning the Great Lakes. The systematic knowledge transfer that had characterized Mohawk ironwork since the 1880s continued unchanged despite the geographic dispersal imposed by the Clan Mother's risk management strategy. Louis had learned to read steel stress patterns through tactile inspection, to judge rivet temperatures by sound and color, and to coordinate with crew members using the precise communication methods that had been refined through generations of dangerous high-altitude work. By June 1930, steel construction had reached the 26th floor, with riveting gangs following closely behind the derrick operations that positioned each massive beam. The pace of assembly reflected not reckless speed, but systematic efficiency that eliminated the delays and corrections that plagued less organized crews. Mohawk workers had developed preparation routines that anticipated potential problems before they occurred, quality control procedures that detected faulty connections before they could propagate into structural weaknesses, and coordination protocols that maximized productivity while maintaining the safety margins essential for survival at such heights. The Empire State Building project attracted hundreds of skilled ironworkers from across North America, but the core crews responsible for the most demanding high-altitude connections were predominantly Mohawk workers whose training traced directly back to the systematic methods developed during the 1880s bridge construction era. These men represented not individual expertise, but a collective knowledge base that had been systematically transferred and refined across multiple generations of dangerous construction projects. Thomas Deere, working his 15th year as a skilled riveter, had developed techniques for detecting potential beam failures that went beyond the visual inspections European engineering standards required. His methods involved running his hands along steel surfaces to identify microscopic stress concentrations, listening for subtle changes in the sound steel made under load, and monitoring the behavior of connections during thermal expansion cycles that occurred as the building heated and cooled each day. This tactile and auditory knowledge couldn't be learned from textbooks, but required direct experience under the mentorship of workers who had refined these techniques through decades of practical application. The construction workforce peaked at 3,500 workers in September 1930, including several hundred Mohawk iron workers whose presence throughout the project represented the successful implementation of the clan mother's dispersal strategy. Instead of concentrating skilled workers on a single prestigious assignment, the booming out rule had positioned experienced crews throughout the American construction industry, ensuring that catastrophic loss could never again eliminate such a large proportion of essential expertise in a single disaster. On September 19, 1930, the steel framework topped out at 1,048 feet above street level, just 23 weeks after the first column had been positioned. The speed of construction reflected not corners cut or safety compromised, but systematic efficiency that European construction methods had never achieved. The precision of connections, measured through rejection rates below 1% for faulty rivets, demonstrated that rapid assembly could coexist with quality standards that exceeded industry norms. Kyle Caron-Hyactatier Beauvais, great-nephew of Jean-Baptiste Beauvais, who had survived the Quebec Bridge collapse, worked on the Empire State Building's upper floors as part of a crew responsible for installing the complex steel framework that would support the building's distinctive setbacks and the mooring mast that extended its height to the record-breaking 1,250 feet. His presence on the project represented continuity with the systematic training methods that had been developed over nearly 5 decades of high steel construction, but also evolution of those methods to address the unprecedented technical challenges that skyscraper construction at this scale presented. The building's structural integrity was tested on July 28, 1945, when a B-25 bomber flying through dense fog struck the 78th and 79th floors at approximately 200 miles per hour. The impact killed 14 people and caused significant fire damage, but the steel framework installed by Mohawk crews 15 years earlier contained the destruction to the immediate impact area. The structural connections held under stresses that exceeded design specifications, preventing progressive collapse that could have destroyed the entire building. Official construction records documented 5 worker deaths during the Empire State Building project, a remarkable safety record for a construction project of unprecedented scope and complexity. The achievement reflected not luck but systematic safety protocols that had been refined through generations of dangerous high steel work. Mohawk crews had developed crisis response procedures, quality control methods, and coordination techniques that reduced both individual risk and project-wide accident rates while maintaining the productivity levels that enabled rapid construction. By 1931, when the Empire State Building opened for occupancy, the systematic training methods that had originated with Mohawk observation of European riveting techniques during the 1880s had become the foundation for American high steel construction capability. The GOAT theory that attributed Mohawk's success to natural fearlessness had been replaced by recognition that systematic knowledge transfer produced consistently superior results compared to formal engineering education alone. The secret had never been the absence of fear, but the development of systematic methods for managing risk while maintaining the precision that structural integrity demanded at impossible heights.